Now I am going to discuss about the losses in a DC generator. Energy neither be created nor it can be destroyed. It can only be transferred from one place to another. In DC machine, mechanical energy is converted into electrical energy. During this process, the total input power is not transformed into the output power. Some part of input power gets wasted in various forms. The form of this loss may vary from one machine to another. These losses give a rise in temperature of machine and reduce the efficiency of the machine. In DC machine, there are broadly four main categories of energy loss. So, first loss is the copper losses. The copper losses are the winding losses taking place during the current flowing through the winding. These losses occur due to the resistance in the winding. In DC machine, there are only two windings. One is the armature, the other one is the field winding. Thus, copper losses are once again categorized in three parts. First one is the armature copper loss, second one is the field winding copper loss, and the brush contact resistance loss. The copper losses are proportional to square of the current flowing through the winding. So, if you consider the armature copper loss in a DC machine, so armature copper loss is equal to Ia square Ra, because Ia is the armature current flowing through the armature, Ra is the armature resistance. The square of the current is nothing but Ia square. So, total armature copper loss is Ia square Ra. These losses are about 30% of the total full load losses. And the second one is the field copper loss. In case of shunt generators, field winding copper loss is ISH square RSH, where ISH is the field current, shunt field current, and RSH is the shunt field resistance. In case of series generators, the loss is nothing but ISC square RSC, where ISC is the field current in the series field winding and RSC is the resistance of the series field winding. These losses are about 25% theoretically, but practically it is constant. So, the next loss is the magnetic losses or the core, or it can also be called as the iron losses. So, as iron core of the armature is rotating in magnetic field, some losses occur in the core which is called the core losses. Because machines are operated with constant speed, so these losses are almost constant. These losses are categorized into two forms. One is the hysteresis losses, second one is the eddy current losses. So, if you consider the hysteresis losses, this loss is mainly due to the magnetic reversals. So, every portion of the rotating core passes under north and south pole alternatively, thereby attaining south and north pole polarities respectively. The core undergoes one complete cycle of magnetic reversal after passing under one pair of poles. So, the hysteresis loss is given by the Steinmetz formula. So, based on this, omega WH is the hysteresis loss, which in turn is equal to eta Bmax to the power of 1.6 FV watts, where V is the volume of the core, eta is the Steinmetz coefficient, whereas Bmax is the maximum flux density and F is the frequency. So, the loss depends upon the volume and the grade of iron and maximum flux density. So, if you consider the eddy current loss, so when the armature core rotates, it also cuts the magnetic flux. Hence, an EMF is induced in the body of the core according to the laws of electromagnetic induction. So, this EMF, though small, sets up large current in the body of the core due to its small resistance. So, this current is known as eddy current, and the power loss due to the flow of this current is called as eddy current losses. So, the eddy current losses is nothing but initiated as K into Bmax square F square T square V square watts, where Bmax is the maximum flux density, F is the frequency, T is the thickness of the core, and V is the volume of the armature core. So if you see from the two expressions, so hysteresis loss as well as the eddy current losses both are proportional to the frequency. So eddy current losses can be reduced by using a laminated core, but hysteresis loss can be reduced by considering the quotient as minimum as possible. The next loss is the mechanical losses. The losses associated with mechanical friction of the machine are called mechanical losses. These losses occur due to friction in the moving parts of the machine like bearing and brushes, etc. And windage losses occur due to the air inside the rotating coil of the machine. These losses are usually very small, about 15% of the full load loss. And the next one is the stray losses in a DC machine. Magnetic and mechanical losses are combinedly known as the stray losses. So, if you consider the constant losses, the field copper loss is constant for shunt and compound generators. Hence, stray losses and shunt field copper loss are constant. These losses are together known as the constant losses or the standing losses of a DC machine. So, hence if you consider for a shunt and compound generators, the total losses is nothing but variable losses plus constant losses, whereas the variable loss is nothing but the armature copper loss because it varies with the load current. So, the complete total loss of a DC machine is nothing but constant losses plus variable losses. Thank you.